Let alpha be an irrational number, and you consider the points, the decimal part of the n multiple of alphas, where n ranges from the set of the integers. Let me add the definition that this means n times alpha minus the floor of n alpha. And this means the largest integer that is less than or equal to n times alpha. Those points are uniformly distributed in the open interval from 0 to 1. This means for any a and b between 0 and 1, we have the limit where capital N goes to infinity, number of integers between 0 and capital N, such that the decimal part of n alpha that lives in the interval AB divided by n is always equal to the length of AB. And this theorem is called the uniform distribution theorem. Hey guys, today we are going to talk about this famous uniform distribution theorem. The intuition of this theorem is pretty clear. Suppose you have a circle of perimeter 1 and you jump around this circle with increments all equal to alpha, an irrational number. After sufficiently long time, you can imagine your footprints are all over this circle. It's not hard to see that your trace will be dense on this circle. Now, a further question is, are your footprints going to be uniformly distributed over this circle? Namely, given any interval on this circle, is the number of your footprints kind of proportional to this circle when you jump around this for a sufficiently long time? That is basically what this uniform distribution theorem tells you. Now I will start talking about the proof of this theorem, and I will add the reference links below. The proof will be very elementary but also highly technical. It basically only uses the basic number theory, elementary number theory, and real analysis. And the argument involves a lot of counting techniques, which will try to explain it clearly to you. So now let's get started. First, we will need a lemma. Suppose alpha is an irrational number and PQ are two integers that are co-prime to each other, satisfying that the difference between them is less than 1 over q squared. Then, for any I greater or equal to 0 and less than q, there exists a unique j greater or equal to 0 and less than q such that the decimal part of j times alpha is greater or equal to I over q, but less than I plus 1 over q. Okay, so let's prove this. First, assume that alpha is greater than p over q. Then, we know for every j integer greater or equal to 0 less than q, we have j times alpha minus j times p over q strictly greater than 0 and is less than j over q squared by the assumption above, and this guy, because j is between 0 and q, will be less than 1 over q. Now writing jp equal to sj times q plus rj with r sub j between 0 and q. By the Euclidean division of algorithm, we see that first, the floor of j alpha, namely the largest integer less than or equal to j alpha, is equal to s sub j. And let's check this. Indeed, so if you write alpha equal to p over q plus beta, with beta between 0 and 1 over q squared, then j times alpha is equal to j times p over q plus j times beta. And this guy will be equal to sjq plus rj divided by q plus j beta, which is in turn equal to sj plus rj divided by q plus j beta. But if you look at this term, first, it is greater than 0, because rj and q are both assumed to be greater than 0, and j beta are both greater than 0. So they are all positive. So I should emphasize that q here is greater than 0. And this guy is also less than 1, because it is less than or equal to, remember rj is less than q, and beta is less than 1 over q squared. So this guy will be less than or equal to q minus 1 divided by q plus q minus 1 divided by q squared. And you can easily see that this guy is strictly less than 1. And this means the integer part of j alpha will be just s sub j. And furthermore, we see that the decimal part of j alpha, which from the calculation above is equal to rj divided by q plus j beta. And this guy is strictly greater than rj divided by q, but less than or equal to rj divided by q plus q divided by q squared. This follows from the assumption on j and beta. And sorry, this should be strictly less than. And the right hand side will be equal to rj plus 1 divided by q. So the decimal part of the j alpha is bounded by those two numbers. Now the second observation is that we have a bijection from the set of integers from 0 to q minus 1 to itself by sending j to r sub j. So this is the bijection. So let's recall the definition for r sub j. By the definition of r sub j, we know r sub j is congruent to j times p mod q. So indeed, r sub j is congruent to j times p mod q. Now r sub j is greater or equal to 0, but strictly less than q. And since PQ are assumed to be coprime, it follows from elementary number theory that the set 0, p, 2p, all the way to q minus 1p form a congruence class mod q. So it follows that each j corresponds to a unique r sub j in the set of integers from 0 to q minus 1. And this essentially follows just from the congruence relation between rj and jp. And this part gives us the existence of j. And this part gives us the uniqueness of j. So we have both the uniqueness and the existence for j. And this completes the first case when alpha is greater than p over q. Okay, now we deal with the second case. If alpha is less than p over q. In this case, you have p over q minus alpha squeezed between 0 and 1 over q squared. And if you multiply all sides of the inequality, you will get by j, where j is greater or equal to 0 and less than q. And now you know the right hand side must be less than 1 over q. Now write as before, jp equal to sjq plus rj, where rj is greater or equal to 0, less than q, by the Euclidean division. And now let alpha be equal to p over q minus beta, where beta now is greater than 0, less than 1 over q squared. It follows that j times alpha, which is jp divided by q minus j beta, is equal to sj plus rj divided by q minus j beta. And now I want to study the decimal part of j alpha. And there are two cases. First, if rj is equal to 0. If rj is equal to 0, then from here we know jp is equal to sjq. But pq are coprime. So we must have Q divides J. And the only thing that could make this happen is when J equals 0. So in this case, we will have J alpha simply equals Sj, which is an integer. So the decimal part of it is just 0. This is the first case. In the second case, if you have Rj greater than 0, if Rj is greater than 0, then you know that Rj divided by Q minus J beta is greater or equal to 1 over Q minus, you know, J is always less than Q, so this is less than or equal to Q minus 1 divided by Q squared, which is strictly less than 0. And on the other hand, you know this guy is less than R divided by Q, but R divided by Q must be less than 1. So this number is something between 1 and 0. So the decimal part of J alpha in this case will be just R divided by Q minus J beta. Then you will have, then let's study Rj divided by Q minus J beta. First, this guy is less than or equal to Rj divided by Q. And you know this is a number less than 1. On the other hand, this guy is greater or equal to Rj is greater than Rj divided by Q minus Q divided by Q squared, which is Rj minus 1 divided by Q. Remember, J here is strictly less than, J here is strictly less than Q, and beta is less than 1 over Q squared. But you know this guy is greater than 0 in this case. So, as a result, this guy will be equal to the decimal part of J alpha. And now you know J alpha is squeezed between Rj minus 1 divided by Q and Rj divided by Q. And you also know that by this congruence relation, you still have Rj is congruent to Jp mod Q. And you have a bijection from 0 to Q minus 1 to itself by sending J to R sub J. This is a bijection. And all of this tells you for any I greater or equal to 0 and less than Q, there exists a unique J greater or equal to 0 less than Q such that the decimal part of J alpha is greater or equal to I divided by Q, but less than I plus 1 divided by Q.